Hello everyone, welcome to Demystifying Networking, where we demystify complex networking concepts. In this video, we are going to demystify the concept of IP time to leave, which is also called as TTL. When I was studying the concept of IP TTL, I had a lot of questions in my mind, like how TTL works, when exactly the TTL is decremented. Is it decremented at the ingress or at the egress, or when the packet is actually dropped? So if you also have the same questions about IPTTL in your mind, then don't worry. You have reached the right resource that will help you understand answers to all these questions. Let's see what an IP time to leave field is. So TTL is an 8-bit field in the IPv4 header that is used to prevent the packet from looping forever in the network in case of routing loops. As you can see on your screen, the IPv4 header includes an 8-bit field which is called as time to leave. Now that we have seen what an IPTTL field in the IPv4 header is, let's try to understand how the TTL prevents the packets from looping forever in case there are routing loops. When an IP packet is sent by the source device, it has a default TTL value. For Cisco devices, the TTL value is 255. For Windows-based devices, the default TTL value is 128, and for Linux-based devices, the default TTL value is 64. Along the path to the destination, each router decrements the TTL value by 1 when it forwards the packet. If the TTL value reaches 0, the packet is dropped. In such a case, the router that dropped the IP packet, for which the TTL reached 0, sends an ICMP time exceeded message to the originator of the IP packet. To understand how TTL prevents the packet from looping forever in the network in case of routing loops, let's consider a simple scenario. In this scenario, we have three routers: router 1, router 2, and router 3. We are assuming that there is a routing loop among these three routers for the destination IP. It means that the routing table entry on router 1 for the destination IP points to router R2 as the next hop. The routing table entry on router 2 for the destination IP points to router R3 as the next hop. The routing table entry on router R3 for the destination IP points to router R1 as the next hop. So this way, there is a routing loop for the destination IP. To keep the things simple, let's assume that the default TTL value used by router R1 for an IP packet is 5. Router 1 sends an IP packet with a TTL value of 5 to the next hop router R2. Router R2 decrements the TTL value by 1 and sends an IP packet with a TTL value of 4 to router R3. R3 decrements the TTL value by 1 and sends an IP packet with an updated TTL value of 3 to the next hop router R1. R1 decrements the TTL by 1 and sends an IP packet with an updated TTL value of 2 to the next hop router R2. R2 decrements the TTL by 1 and sends an IP packet with an updated TTL value of 1 to the next hop router R3. When R3 receives an IP packet with the TTL value of 1, it decrements the TTL value by 1, and then R3 realizes that the TTL has reached 0, and that is why R3 drops the packet and sends an ICMP time exceeded message to the originator of the packet, which is router 1. So this way, the IP TTL field prevents the packets from looping forever in the network in case of routing loops. Now let's see how the TTL value is handled by the router when it receives the IP packet. When a router receives an IP packet, it first checks if that IP packet is destined to the router itself. It does so by comparing the destination IP address with the IP addresses configured on the router's interfaces. If the router determines that the packet is destined to the router, it processes the packet locally because the packet has already reached its destination. If the router determines that the IP packet is not destined to the router itself, the next thing it checks is the TTL value in the received IP packet. If the router determines that the IP TTL value in the received packet is not greater than 1, then the router decrements the TTL by 1 and drops the packet. It also sends an ICMP time exceeded message to the originator or the source of the IP packet. But if the router determines that the TTL value in the received IP packet is greater than 1, it does a routing table lookup for the destination IP and also finds the next hop MAC address. The router then decrements the IP TTL value by 1 and computes the IP header checksum. The IP header checksum needs to be recomputed here because the IP header is updated with the new TTL value, and that's why the IP header checksum needs to be recomputed. Next, the router encapsulates that IP packet in a frame and sends it to the next hop. Now, let's see some examples that will help us understand how TTL is handled by the router when it receives an IP packet. In this first example, let's assume that the IP packet has 2.2.2.2 as the destination IP address and has a TTL value of 1. When the router receives an Ethernet frame, the router decapsulates the IP packet. The next thing that router does is verifies if that IP packet is destined to the router itself. In this case, the IP packet is destined to the router as the destination IP address 2.2.2.2 is one of the IP addresses configured on the router interfaces. As the IP packet is destined to the router itself, it has already reached its destination, and the router then processes that packet locally. In the second example, let's assume that the destination IP address of the packet received by the router is 10.2.3.2 and the TTL value is 1. When the router receives an Ethernet frame, it will first decapsulate the IP packet from the frame. The next thing that router does is verify if the IP packet is destined to the router itself. In this case, the IP packet is destined to the router as the destination IP address 10.2.3.2 is one of the IP addresses configured on the router interface. As the IP packet is destined to the router, it has already reached its destination. Router then processes that packet locally. In the third example, let's assume that the destination IP address in the received IP packet is 4.4.4.4 and the TTL value is 1. When the router receives an Ethernet frame, it will decapsulate the IP packet from the Ethernet frame. The next thing the router does is it verifies if the IP packet is destined to the router itself. In this case, the IP packet is not destined to the router as the destination IP address 4.4.4.4 is not one of the IP addresses configured on the router interfaces. As IP packet is not destined to the router, it must be routed. But before making routing decision, the router checks the TTL value of the received packet. IP TTL in this case is not greater than 1 since the TTL value in the received packet is 1. The router then performs the following actions. It decrements the TTL by 1, which makes the new TTL value to 0. As the TTL value becomes 0, the router drops the packet and sends an ICMP time exceeded message to the source. In the fourth example, let's assume that the destination IP address of the received IP packet is 4.4.4.4 and the TTL value is 6. When the router receives an Ethernet frame, it decapsulates the IP packet. The next thing that router does is verify if the IP packet is destined to the router itself. In this case, the IP packet is not destined to the router as the destination IP address 4.4.4.4 is not one of the IP addresses configured on the router interfaces. As IP packet is not destined to the router, it must be routed. But before making a routing decision, the router checks the TTL value of the received packet. In this case, the TTL value in the received IP packet is greater than 1 since the TTL value in the received packet is 6. The router then performs the following actions. It does the routing table lookup for the destination IP to find the next hop and the exit interface. The router also finds the next hop MAC address. The router then decrements the IP TTL by 1 and recomputes the IP header checksum. The IP packet with updated TTL value of 5 is then encapsulated in an Ethernet frame and the frame is then sent to the next hop. I hope this video helped you in understanding the concept of IP TTL. Please like and share this video and subscribe to Demystifying Networking for more such useful videos.